Can people hear me on Zoom? Daniel, can you hear me? Okay, good. Jeff and Jianren.
What?
Jeff and Jianren.
Oh, we're here.
Yeah.
Oh, great. Oh, that never happens. Oh, I have you guys contact the profile or you are each other have class. Does it feel like only half is so class or you're getting more than half? It's just not way. Yeah, it's only the very bottom of the class. You always only get half credit. Yeah, I would encourage that very much that we could do it half class. Unless you can negotiate for it somehow. Oh, you're gonna be teaching this at the full class and teaching? And then you should, yeah, I would not do it in the future of classes. Do the transition into a full class. If you can do that, then.
Go do that.
It's about time. Shall we get started?
Wait, 1 minute after. These people's clocks are about 1 minute off.
Yeah.
Analog clock. Yeah, or annual clock.
Yeah, that's.
Yeah, I guess if they're all things to the clock. Okay, yes, you can start. Okay, hi everyone, it's my pleasure to introduce the dispense Carrie. Please write down, thank you. Carrie been a master student in my lab for the last 2 years. Anyway, following the standard protocol of master's expenses, please keep clarification questions. Please only ask for burning clarification questions during the talk and keep longer questions to the end. Great. Go ahead.
Thank you, Professor Hill, for the kind introduction. My name is Harry. I'm a MSR student, and today is my thesis talk. The title of the talk is Seeing in 3D Towards Generalizable 3D Visual Representations for Robotic Manipulation. So the motivation of my work has been, object-centric visual representations. So why do we care about object-centric representations? Because they are very useful in many robotic manipulation tasks. And they are, again, a key component in learning visual motor skills. But the problem with, visual representations, or the difficulty with such, is that they are really hard to generalize beyond a limited set of objects. And another motivation that we built our work upon is we mainly focused on 2 major object categories. First being articulated objects, and second being free-floating objects. Articulated objects are objects that are connected by articulated joints, and we call such objects articulated because they can be articulated using the joint, and they are usually constrained by the part so that they only have 1 degree of freedom. And free floating objects are they're not constrained by any kind of articulated parts, so they have 6 degrees of freedom, X, Y, Z, and RPY. Right. So building on top of the motivation, we published 2 peer-reviewed papers and for articulated objects and free floating objects, where we developed 2 separate generalizable visual representations for those 2 categories of objects. So let's start with articulated objects. So articulated objects, how do we get rid of this? Articulated objects, to learn useful visual representations for articulated objects, we learn 3D articulation flow as a generalizable representation. So the TLDR is that using 3D articulation flow to manipulate articulated objects, we can bypass the needs to estimate articulation parameters. And such system works well in the real world and generalizable across a wide variety of objects. So let's dive in. The paper that we present, or the work that we did, is called Flowbot 3D, learning 3D articulation flow to manipulate articulated objects. This is a joint work with Ben and Dave. Right, so articulated objects are everywhere. For example, when you're opening a doorknob, and also door itself, they are revolute objects because they can only revolve about an axis. And drawers, they are prismatic objects because they can only slide on this sliding axis. And fridge doors and laptops, flip phones, and also staplers. Articulated objects are everywhere in our household scenarios. And as humans, we can estimate how objects can articulate by just looking at them. So like, for example, you might not have seen like the exact same copies of these objects in your lives, but by just looking at them, you might be able to hallucinate how each articulated joint might move under articulation. So this is just based on our past experience and also our ability to imagine how parts might move. So we want the robots, or like some kind of robots policies, to do the same thing. Common approaches to robot learning such tasks of manipulating articulate objects include first end-to-end approaches, where you have an observation of the object, some kind of observation, and you use the neural network to do all the heavy lifting and output low-level actions for the robot to actuate the object. And the advantage of such approach is that it optimizes the task objective very straightforwardly, but it's hard to generalize well to other objects. And the second approach that people have usually done before is modular approach, where you first have this observation, and then you run segmentation on top of that to know which parts could be manipulated or actuated. And then you run connectivity structure and also articulation estimation to estimate how the parts might move, right? And after that, you run motion planning to give you like a feasible motion to manipulate the part. And the pros and cons is that the pros is definitely better generalization when it works, but again, like there's too many potential points of failure, so it's kind of brittle if any of these components just breaks for some reason. How do we get the best of the both worlds? So our approach is that we take inspiration from both, and we estimate affordances first, and then we run motion planning on top of that. So it's closer to the end task objective, but also had this nice residual component in it. And the pros and cons is that we have fewer failure points here. There's only 2: articulation parameter, affordance estimation, and also motion planning. And it optimizes closer to the end task, because sort of like end to end. And as you can see later, it has better generalization versus end to end approaches. But the difficulty here is that we must choose the right affordance to learn. How do we learn such affordance? So the key question we're trying to answer is, what kind of affordances do we want to predict? For prismatic joints, for example, drawers, it's pretty straightforward, right? Because you only have one direction to move the part. So if you apply force in this direction of the degree of freedom, then you have the most efficient policy to move this drawer. For revolute joints is a little bit more complicated, but again, like if you parameterize the revolute joints by this, rotation axis and origin, if you apply a force perpendicular to this axis, right? And if you apply a force further away from the axis, then you get the most leverage. So intuitively, it just means that if you open a door, if you apply a force, a pulling force on the hinge, it's very hard to open a door, right? But if you apply the force further away from the hinge, say like on the doorknob, that's gonna be a lot easier. So that's my that's our intuition, and we use physics to prove that this is indeed the most feasible, or like the most leverage that we can get using Newton's second law. So what we need to know here, based on the two intuitions, is that first, what direction should we apply the force in, right? So for prismatics, just parallel to the direction of degrees of freedom, and for revolutes, just perpendicular to the rotation axis. And also, what points on the object have the most leverage, right? Prismatic doesn't matter that much, but revolute, you should be farther away from the rotation axis. So we proposed a affordance called 3D articulation flow, or 3D-AF for short. So 3D-AF, it assigns a 3D vector to each point on the object, right? So it's a dense 3D vector field that assigns a 3D vector to each point in your point cloud observation, whose direction is how that point moves, how the point that gets assigned moves under instantaneous articulation. And the magnitude is the relative leverage for that point, right? As you can see here, as expected, the leverage further away from the hinge should be way more than the leverage on the hinge. And the direction to which each vector points represents, the direction under instantaneous articulation. So all the robot needs to do is to grasp a point. First choose a point and then follow the flow, follow the direction of the flow. So to predict 3D articulation flow, we use ArtFlowNet, which is as follows. So first you have a point cloud observation of the scene, and then you pass the point cloud observation into a point plus, a standard backbone, which is segmentation that takes its input endpoints and outputs, endpoints. And then each of the n vectors represents each point's articulation flow. And you have this predictive flow field. And to train it, we use ground truth flow that can be easily calculated using forward kinematics from your simulation, right? And then you can calculate the ground truth flow from simulation, and then you run MSE loss on top of that to train this neural network. So using 3D articulation flow, we devised this system called Flowbot 3D. So Flowbot 3D is a robotic system that uses 3D articulation flow to actuate articulate objects. So here's how it works. So you get a partial point upon observing the scene, you get a partial observation, right? Point cloud observation. So it's dense and might be cleaned for prettier input, right? And then you feed that into your ArtFlowNet to get a 3D dense articulation flow, which is our visual representation here. And then in the first grasping phase, you need to select the point. So how do we select the point? Usually simple heuristic works pretty well here, as I will describe after I finish describing this whole pipeline. And then you run motion planning, off-the-shelf motion planners such as OMPL, and you just attach the gripper to that point. We use a suction gripper here, but parallel jaw also works. And in the articulation phase, once you select that point, once you make a contact with the object, you're now rigidly attached to the articulated objects. And then you would just try to actuate the objects by following the flow direction, right? And then you would just first select the flow direction and then use motion planning to follow that flow direction. And then you will close the loop, right, and repeat, right? So this is a closed loop step that runs, every time step in your whole pipeline. And so how do we select the contact point? Well, in practice, in simulation, you can just attach a force to it, so it's rigidly attached in pi bullet. But in the real world, we would first, try to estimate the curvature of the object as a heuristic for graspability. and then we can select, graspable points with low curvature. So that's a very simple heuristic that works pretty well in the real world. And we want to emphasize that this is one model trained on all training categories. So we use Sapien as our Sapiens partner mobility data set as our data. We have 499 training objects from 11 categories. So we use simulator to generate ground truth, 3D articulation flow. And we have 10 unseen categories, 238 objects in simulation. These are completely unseen categories, right? And we also test on seen categories, but unseen instances, both in simulation. And in the real world, we test on 15 objects, which are totally unseen. And in the real world, we have a physical setup. The setup is as follows. We have a Sawyer Black robot that has a suction gripper, and we use Azure Connect as our visual input to capture the depth images and which we can get point cloud from, and also an object that we're trying to articulate. So here's a quick sneak peek of the results where you see like the robot's trying to open a bunch of different objects. There are 12 real world objects here, right? And you see that the two jars, they're not technically articulated objects, but we sort of treat them as prismatic objects because they you can't think of the lid as sliding on this axis, right? So to measure how effectively we can articulate the objects, we measure the success rate, where the success is defined as opening more than 90% of the way. And in simulation, we compare with the following baselines: end-to-end approach, screw parameter, articulation parameter prediction, and UMPNet, which is a paper from Jianren's group, and Flowbot beats all three baselines. And also Flowbot performs pretty well on test categories too. So more than 70% of the time you can open more than 90%. And in the real world, we also test on end-to-end approach, whereas there's only one behavioral cloning agent that's trained in simulation, try to, without any fine-tuning, try to test it in the real world. And we also test our method without any fine-tuning in the real world too. So you might wonder, what does predictive flow look like? For training objects, for example, this is a drawer, and also test objects. This is dishwasher. You see, like across frames, our articulation flow field is pretty consistent across the frames, right? There might be some cases where it's wrong, but it gets the rough sense of like how that part might move, how the point might move under this instantaneous articulation. So that helps a lot with the actual motion planning phase. And another question that you might want to ask is, why does Flowbot 3D transfer well from simulation to the real world without any fine tuning? So this is because synthetic point clouds and real world point clouds, they look very similar, right? On the left, you can see a synthetic point cloud that we capture from the simulation. On the right, you see a real world point cloud that we actually capture using our Azure Connect, camera. So this is a very small domain gap to deal with. That's another motivation to use point cloud in as your visual input. And 3D articulation flow is a dense object-centric representation. So it's object-centric, so it doesn't need to capture the similar dynamics, which is usually a bigger domain gap, right? So I'll show you some real-world trials here. So we compare Flowbot 3D with end-to-end behavioral cloning in machine learning, right? And again, like end-to-end approaches and like end-to-end imitation learning just completely fails in a lot of cases. And again, like keep in mind, this is one model for all of the objects. We train the model in simulation and testing in real world without any fine tuning. Right, and yeah. So in summary, we propose Flowbot 3D, which estimates 3D articulation flow and uses motion planning to articulate novel objects in both simulation and the real world. In terms of performance, Flowbot 3D significantly outperforms end-to-end learning, and it avoids the brittleness of modular approaches so that it has like fewer points of failures. And we can generalize to unseen objects and transfer to the real world without any fine-tuning and retraining. Right. So that's it for articulated objects. So we propose one possible visual representations for articulated objects. So the next category of objects that we are interested in is free floating objects. So how do we represent visually those free floating objects efficiently in robotic manipulation tasks? So we propose a mathematical concept called cross poles. So in order to represent those objects, we learn the cross poles as a generalizable representations across different objects. And the TLDR is that so learning cross poles can bypass the needs to estimate individual 60 object poses, and it works well in the real world and generalize across a variety of objects. So this is the Coral paper that we submitted that was accepted last year called task-specific relative pose estimation, or TAX pose. This is joint work with Chur, Brian, and Ben. Let's talk about relative transform or cross poses, right? So why do we care about relative transforms? We say that in a lot of robotic manipulation tasks, relative transforms are very important because the definition, the very definition of the success of the task might depend on the object pose relationships. For example, if you're trying to put this pie in this oven, right? You put it in, right? And once the pie is in the oven, this defines a relative transforms, a relative transform between the pie and the oven, right? And that transform alone can define this task success. And if no matter where their initial poses are, as long as you can move these two objects according to this relative transform, you can successfully manipulate this object, right? So you can you can get a success by just achieving this relative transform. And similarly for a mug hanging task, where you have a mug and you're trying to put it on the rack, right, on the peg of the rack. So the mug and the peg itself defines a relative transform, and no matter where the mug or the rack is, before you try to manipulate them, as long as you can put them inside, as long as you can put the mug inside the peg like this, then you achieve this relative transform, which is a success. So right, this is the importance of relative transforms, and using this intuition, we want to mathematically define cross poses or relative transforms or relative poses in robot learning. So we call our mathematical concept a task-specific cross pose, which is estimated as a function of both objects' point clouds. For example, it could be any model, but we're using neural network, right? This neural network takes as input 2 point clouds, PA and PB, right? So here, PA is what we call the action point cloud, which is the mug here represented in the blue points. And we also have an anchor point cloud, which is gray here, right? So that's the anchor. And the network takes as input those 2 point clouds and outputs a SE3 transform, right? In 60 pose for the relative pose. So here, the 2 point clouds are in their goal configuration, meaning that this is the pose, the relative pose that we want, right? This is my goal to accomplish this task. So in the goal configuration, my cross pose, my task pose should give me an identity transform, right? This is also in the goal pose, right? Because if you're transforming the 2 objects simultaneously using the same transform, it should also be the goal configuration, right? So this should also be identity. And if you rotate that and translate that together, that's still in the goal configuration. And if you transform the mug by T alpha, right? Then this cross pose should give you T alpha, right? Because you also need to transform the mug rack by T alpha in order to achieve this pose, the goal pose, the goal configuration. And if you start with the mug transformed by T alpha and the rack transformed by T beta, right? The cross pose should give you T alpha, T beta inverse, right? Because you need to first transform the rack back to its canonical form, and then like then to the mug frame, right? So it's T alpha times T beta inverse. And to bring the mug to the mug, right, you just take the inverse of that, right? You just take the inverse of T alpha T beta inverse, which is T beta times T alpha inverse. Right, so that gives you the goal configuration. So we aim to learn a model that has this property. So how do we learn relative poles? How do we train tax poles network? Well, we propose a tax poles estimator that takes as input the 2 point clouds and output is tax poles SE3, right? This is very different from what you have seen before, where you independently, estimate the 2 objects poses, right? And then like somehow like get the relative transform using like using like those techniques, right? So instead of estimating the poses independently, we try to use attention and try to use correspondence to get the actual tax poles. So we learned the relative pose estimator from correspondence. So why do we use correspondence? Because if you have this initial observation, right? So the action point cloud on the left, anchor point cloud on the right. And you somehow like know the goal configuration, right? Somehow you know the actual goal configuration of this task. You can just construct a one-to-one correspondence between the starting action point cloud to the goal configuration. And from the configuration, you can use like say SVD to reconstruct the SE3 pose. So the correspondence is the key here. We are trying to learn this one-to-one correspondence. So how do we learn it? First, we would featureize the action and anchor point clouds, right? And then we use attention to get a soft cross-object correspondences. But again, like notice that since attention is just kind of dot products, so it's linear transformation, so it's convex, right? So the featurized points would just be limited inside this convex hull of the anchor point clouds. That's not what we want, right? Because some points might be lying outside of the convex hull. So on top of that, on top of this soft correspondence from attention, we would also correct that by adding a correspondence residual, right? So adding these 2 vectors together would give me the corrective virtual correspondence. And we run that for every point, right? So for every point, we get a virtual correspondence. And also notice that like not all the points are equally useful, right? The intuition here is that if you're trying to put a mug on a mug rack, the points on the handle of the mug should matter more than the points say like on the rim. And we somehow want to learn this importance as we learn the tax poles too, as we learn the correspondence too, right? And then this learning importance weights will be used in the later SVD step, so that you're doing this weighted SVD, right? So you're trying to get those more important points more right if you're trying to reconstruct the pose from using SVD. And here's our network structure, right? So you have a action point cloud, you have a anchor point cloud, right? You encode them both point clouds and get embeddings. And run transformer to get across attention, right? So that's your phi A and phi B, and also the weights. And using the weights and the embeddings, you will get the virtual points, the corrected residual flows, and also the importance weights. And then you will feed everything into a weighted SVD to recover the full 60 pose. Now I will talk about each step in more details later. So our correspondence are calculated from attentions, right? So in transformer, we take this multi-head attention, and we run this cross attention, right, to produce the soft correspondences. And basically, the first step that we get is this very first virtual corresponding points. They are actually the weighted sum of your anchor objects, right? So again, like that's inside the convex hull of the anchor objects. And then we use the featurized point clouds to get the importance weights as well as the residual corrections. And the actual adjusted virtual correspondence would just be the soft correspondence from inside the convex hull plus the residual correction, right? So that's VA, which is W times PV plus the residuals. Right, and to train our network, we use 3 different losses. So first we have a demo, right? We have a demo of this test-specific cross pulse, which is the action point cloud relative to the anchor point cloud, but they're in their Go configuration. And again, like we have this segmentation beforehand so that we know like which points belong to which object. And we apply random SE3 transform to both mug and the mug rack, both the action and the anchor objects, and to get the training data, right? So from one demonstration, we would get a bunch of different training data points. And then once you transform the 2 objects, we would first estimate the correspondence and then the corrected correspondences and also the importance weights, and run weighted SVD on top of that to get the cross pulse. And in the training losses that we use, there are 3 different losses. First, we call this point displacement loss, right? So you have a ground truth pulse and also your estimated cross pulse. And your point displacement loss supervises between your estimated pulse and the ground truth pulse after your SVD step. So it would transform the action object and then like do a per point L2 loss, right? To supervise the point displacement. And you also have this direct correspondence loss, which supervises between the estimated correspondences and ground truth correspondence before SVD. So before a SVD step, you have your your TAB times your PA, right? That's your ground truth correspondence, right? That's your action object in the ground truth go pulse. And you want to make sure that the distance between that ground truth pulse is very small, right? From the distance from that ground truth pulse to the correspondence, virtual correspondence V tilde A is very small. And the third loss is between estimated correspondence before SVD and the resulting cross pulse after SVD. So how do we do that? It tries to make the predicted correspondence consistent with my actual output of the pulse, right? So it minimizes the distance between the virtual correspondence points and also the transform points after applying your estimated cross pulse. So the final loss that we use is a weighted sum of the 3 losses. To recap, we use ground truth pulse to supervise the per point displacement loss, and also the correspondence consistency loss, and before and after SVD loss. Right. So how do we use tax pulse? Using tax pulse at inference time turns out to be pretty straightforward. As long as you have a segmented point cloud of the action and anchor objects, you can feed them into tax pulse estimator, which will give you a estimated cross pulse, right? And once you have this estimated cross pulse, you can then run an off-the-shelf motion planner, right, to achieve that pulse. So why is that? For example, if you somehow get this correct estimated cross pulse, right, and if you have a motion planner that rigidly attaches the robotic gripper to the mug, the mug and the gripper becomes rigidly attached. So to accomplish this task, you can just feed this cross pulse right into the robot, and the robot can accomplish the task to bring the mug into the desired configuration, right? Because they're rigidly attached. And as you can see here, once they're rigidly attached, it just runs it off the shelf motion planner to bring that into the go pulse. You can use tax pulse to learn relative transforms to manipulate unseen objects. For example, if our network just given a few examples of objects in the final configuration, right? And using the data augmentation, the arbitrary transformation trick, you will get a bunch of data points, and then we try to test the trained trained model directly on unseen object instances. For example, here we test on different unseen mugs in simulation. And to test our algorithm, just to test our task-based model, we have two different tasks. The first task is what we call mug hanging task. It's a two-part task because there are two set of task poses that you're interested in. The first is the gripper to mug pose, and second is mug to rack pose, right? Because gripper to mug, you can also think of that as a trying to accomplish a relative pose between the mug and the gripper, right? So the first task pose to predict is the gripper to mug task pose. And the second one is once the gripper is originally attached to the mug, how do you bring the mug to the mug rack? So that's two task poses to predict. And we train on 10 different demos of each task and test on 12 unseen mugs in simulation here. And in terms of results, our method generalizes to unseen mug instances and poses with only a handful of demonstrations, right? So in simulation, we're able to achieve successes under different initial poses and under different geometry of the mugs. And we're also testing the real world. For example, you see like a variety of different mugs being hanged to the mug rack, right, in this video. This is again trained in the real world, right? So we only take about 10 demonstrations in the real world and then segment the point clouds and using the same data augmentation trick to produce the training data. And right, so it generalizes pretty well to unseen poses and also unseen mugs in the real world. And this is a fun video that I did, which is one cut, like no editing, just like run task pose in sequence to produce these results. Right, and to compare, for mug hanging, to compare our method with baselines, we compare with dense objectness and neural descriptor fields. But again, like those two baselines would require the rack to be in the same position across different data points, across demonstrations. So to actually compare with those baselines, we would limit ourselves so that we put the mug rack in the same pose for all demonstrations. And the results that we get, again, like we measure task success rate, and again, like we outperform the NDF and dense objectness for both upright pose and also arbitrary pose. And we also blade on the number of demonstrations here. So again, like results have shown that under the same number of demonstrations, we often perform better than these two baselines. And the next task that we evaluate our method on is called objects placement task. Again, like we're using a subset of the part net mobility data set that was used in Flowbot 3D, where we train on 54 part net mobility objects across 8 object classes in simulation. And we test on 4, and again, train on 4 semantic goals shared across all object classes, which is inside, on top, and also left or right. Right, and so inside just means I want to put something inside something, and on top just means I want to put something on top of something, to the left, the right, similar. And we test on 14 part net mobility objects in simulation and 3 objects in the real world, right? Right, so here's the demonstration, right? We are trying to put the action object inside the anchor object, right? And this is we're using the model trained in simulation. This is without any fine tuning, tested in real. And on top of the objects, again, like right, you're trying to put this bowl or like the cube on top of the oven or the drawer. And so left of the object, right? And so the baseline that we tried in mug hanging task, they're not very viable here because the anchor position varies between examples, right? So instead we test against end-to-end behavioral cloning, which supervises using a full expert trajectory which is generated from motion planning, off-the-shelf motion planning method called OMPO, right? And then based on full point clouds, and like each action is a 60 relative pulse. And we also have this trajectory flow, right? So it's a dense version of the end-to-end method, right? Instead of using this 60 pulse as our method, we as our action, we would use like the point displacement, the flow vectors as our action. So that's a dense version of end-to-end variable cloning or end-to-end dagger. We also have a more concise version of trajectory flow, which is what we call goal flow. So it directly predicts the dense flow vectors from the starting pulse to the final pulse, right? So trajectory flow is per step flow, and goal flow is O0 to OT, O capital T. Right, and in simulation, if you average over all objects, again, like text flows would achieve lower translational error and also lower rotation error. In the real world, though, we achieve more success than goal flow, right? Goal flow was the strongest baseline for across all these baselines. So we compare it with goal flow in the real world. And why we might be curious about like which components actually mattered in our system, in our method. So if we ablate the choices of each individual component, you can see that without the residual correspondence, meaning that without the correction bit, it degrades by 3%. Without the weighted SVD, is going to degrade by without the importance weight, it's going to degrade by 8%. And without attention, meaning that you don't have this cross attention bit, it's going to degrade worse, right? It's 20% drop of performance. Because we're using 3 different losses, we're also interested in what kind of losses mattered here. So if you don't have the direct correspondence loss, it's like small drop of performance. And without the corresponding consistency loss, which is supervises between before and after SVD, there's like a 13% drop. And what really matters here is this per point displacement, per point supervision, right? Which means that I'm trying to directly supervise my my final flow final point cloud output. So the key takeaways here are, so as we're learning cross-object correspondences, such representation allow learning of part-level interactions that generalizes across different objects and initial configurations. And again, like if you have this learned importance weights, which represent how important each individual points are, it will let the network focus on the parts that really matter. And also weighted SVD adds robustness to the dense estimations, right? Because you use SVD to recover the SE3 transform. So in conclusion, we proposed 2 different visual representations for learning generalizable. We proposed 2 different methods for learning generalizable 3 visual representations. So for articulated objects, we talked about Flowbot 3D, which is a dense, per point affordance. And for free-flowing objects, we use taxables, which is to learn cross objects correspondence in a robust way. And both are very generalizable across a wide variety of objects. And you might want to ask, can we combine the 2 to get more flexibility? And the answer is yes. You can see my thesis for the full in-depth mathematical derivation behind that. It's a very long, math equation, but it's doable. Right, and thank you for I would thank my collaborator Ben, my mentor sitting right here. Thanks so much for your help, and Brian and Chor for the collaboration, and also my thesis members, Professor David Hall, Jeff, and Jianren. Thanks so much for your help, and this is the end of my talk. Please feel free to ask questions.
Great. Let's start first with many questions. Jianren,
Yeah. Can I go back to the first one? So my question is, do you use an open loop controller or a closed loop controller?
for the
action card.
for the
So if
for
I need-
Flowbot, right?
Yeah, for Flowbot.
Well, for okay, so for Flowbot, it's sort of like a hybrid, right? So it's open loop in that once you input this flow direction, you would just let it run. But it's closed loop in that you run this, you estimate the flow and then let it run for every step. So each step is open loop, but you close the loop by running that like sequentially.
So my question is it object properly occluded by the robot?
Right. So right. So the points are indeed occluded by the robots, and we found that the occlusion doesn't hurt our performance that much, as long as you can see like the actual geometry of the objects. And in test time in the real world, we're running this URDF filter so that you would use the URDF model of the robot to filter out the robot's points from your observation.
So the next question may be a little bit detailed. What coordinate frame are you using for this kind of problem?
Just world frame. And so in world frame is the say like in your Arvis, right? Your ROS, right? You have this world frame. That is different from what we see in simulation, right? So we would first like do some pre-processing to match the frames and then project it back. This is to minimize the domain gap.
You just scale the objects or normalized object or just like
Like they should be very similar in scale with respect to the simulation. So there's no need to scale it up or down.
Jeff,
Yeah, so great work, great presentation, really good. I'm curious, I'm actually happy you stopped on this slide because this is where my first question was. The fridge on the upper right, it like yanks the fridge.
Right.
Why is that?
Right. So yeah, like Jianren asked me this question before. Well, it's mainly because I didn't write a like a good enough controller such that it interpolates between the two flow steps. Well, for example, you have so T1 it has this directions flow, and T+1 it has another direction, right? Like it's somehow like kind of jerky between the two steps. So I didn't write a very good controller to control that. But again, like it's not the fault of the full prediction. It's more like my fault. I didn't write a good enough controller.
So would you have to move slower?
Right, like slower, and also like adjust the angle of the alignment, right? Because you're trying to align the end effector to the flow point, to the flow direction.
And I guess so. This sort of leads to my next question. What are the failure cases? When did you find this?
All the failure cases. Yeah, like the almonds, they fail pretty miserably in both simulation and in the real world. Almonds. Yeah.
Ovens.
Yeah. We don't have oven demonstration here because it completely failed. And right, and then also like yeah, basically if you another failure case is that there might be some ambiguity, right? For example, if you just look at the fridge here, the fridge could have like this sort of French door style, like two door, right? It could also be just one panel and trying to open from the very left or very right. So that's the ambiguity here. And another failure case is sometimes the flow prediction is going back and forth. So like it doesn't have this sense of which direction actually output. So it's going that way and this way, that way, this way.
Okay.
Yeah. But we have some follow-up work that could solve that. Yeah.
So one last question on the expose. It seems like you're moving in the direction of continuously applying expose in some of your results. I'm sort of wondering, what are the next directions for expose? Like scaling this to, how do you scale this to like a large amount of data sets or things? Do you have to always set up a simulation? You're looking at, or could you do this?
Yeah, that's a very good question. So the question was, what are some future directions for taxables? there are two things that we're working on right now. So the very first is about the underlying assumption of taxables, where we're just assuming that there's only one transformation, one relative transformation between the two objects, which is not always true, right? Because, for example, the pi example, like the pi could rotate and you could put it like anywhere in the oven as long as you put it in. So Jenny from my lab is working on this VAE version, or like the probabilistic version of taxables, such that it can output distribution of 60 pulses. And another thing is regarding how do we use taxables, like how do we further use taxables in a non-continuous way? Is that okay? Yeah, right. So we are looking at the possibility of using taxables as a geometric suggester in a planar. So we could use taxables to suggest, different states for the planar to take. So that would still require some simulation, but again, like taxables is more like a mathematical concept that you can that has some nice properties. But again, like if you're trying to train taxables, you would need demonstration. But that's the neat thing about taxables, right? You just need demonstration. You don't need like the actual data points, which can be arbitrarily generated from say like your simulation.
Great. So I'll just ask a couple of questions. First, can you expand on why does it perform so poorly on ovens?
Right. Yeah. I think ovens. This is more like, okay, like in the real world, never succeeded because the oven looks very different from simulated ovens. In that like the turn knob is like vertical, but like in simulation, the turn knob is like somehow like horizontal. That's my guess. And another thing is in simulation, right? In simulation, we have never seen a door that opens like this. It's always like left to right. Yeah, except for ovens. But we also have dishwashers which perform pretty well. I think it's just because like the geometry of the oven is too complicated at the top. So it somehow confuses the network.
Sure. Okay. Do you have any thoughts on how to fix the oven issue?
Like my thought would be like, just adding more training data and
More ovens?
yeah. Yeah, that's like a brute force solution, right? And another thing is like I tried, what's it called? The Flowbot V2, right? Right. So we developed Flowbot V2, which is another representation on top of this dense flow. We also try to predict a dense version to estimate the articulation parameter. And once we have the articulation parameter, we can run that in an MPC style, because you can just like hallucinate the trajectory like from the start to the end. And once you can have this MPC style controller, you can just do trial and error. Right. So it's like you would have a more flexible interaction capability with those objects.
Yeah, I'll open it up if the audience has questions.
One question I had was, I guess, like on the door ambiguity problem, that's like a problem that humans have also. And like architects have done a lot of research into how do you like visually signal to somebody like which side of the door they should push or pull on.
Right.
And there's been a bunch of like gaze tracking research to like, oh, like when someone's walking up to a rectangular piece of glass, they look like first on this edge or hinges in the middle or like a little square like thing that says push or whatever. But that's not really geometry based, and it's not really generalized. There's like that specific semantic like understanding of this push square inside you push it. Do you think that might help with like an oven handle that looks a lot like a fridge handle, oven has hinges? I guess, do you think there's any value in like semantic information?
Right. So the question is, does semantics add any value to articulated objects manipulation? I think the answer is yes. Our method, Flowbot 3D, focus on a sort of coarse level of manipulation where you don't care about like say like how the doorknob might articulate, right? You only care about like actually opening the door. So if you can somehow understand, individual parts better, meaning that like once I see this doorknob, I know I should first rotate the knob, right? And it's either push or pull once you twist the doorknob. That would be like, I would say like a more flexible policy, right? But again, this is a very valid point. We currently don't support that, but in terms of future work, it's very worth trying.
Other questions?
I think Henry had a question regarding his project.
Yeah, recently, radio paper, I was curious, like a very creative question for consider working. So there's like a two articulated part, first is the hinge and then the door. So do you think it's possible to use this kind of robot flow prediction? So as let's say we have two stages, and the first stage, the flow should be the going downwards, and then you open the door and the flow change the direction. If it's non-horizontal possible, do you have any?
Right. So the question was, how do we use Flowbot in a more generalizable setting where there could be multiple articulated parts? Well, like Flowbot, like I think the main contribution of Flowbot here is first is to this affordance learning, and second is like there's very easy motion planning on top of this affordance. But there could be also other alternatives to this motion planning part, right? You could run your flow. You could have another controller that at each time step you would run your Flowbot sequentially, right? Just to understand which part of the objects could be moved, right? And then like execute the point sequentially, execute the flow sequentially. So that would involve learning or estimating flow in a sequential manner. But it's doable if you're using a dense flow. So I was like the answer lies within the domain of what kind of planner you want to use, right? Because again, like Flowbot 3D, it proposes this this new visual representation, but how do we use that visual representations to help the robots plan, right? That's an interesting direction to pursue.
So I see both of your works using point cloud as observation. So for what kind of tasks do you think point clouds are the best?
Right, and point cloud, we chose point cloud because that's Professor Hill and our lab's philosophy, always use dance representations. Right, so again, like I think that's a very good question. So what kind of scenarios do point clouds fit the most? One is definitely like if you care about like the per point affordance, or like if there's like a how do I say, like if there's like if the geometry of the objects cannot be seen using pure like RGB signal, then you would better just use like point cloud, right? Or depth, something like that. And one bad thing about point clouds is that the 3D models for processing and embedding the point clouds, they're not as scalable as ResNet or like any 2D RGB architectures. So that's like the trade-off you want to be aware of. Right, and I would just say like you could use some other representations too, but point clouds, they are flexible and they have some nice mathematical properties that also preserves the geometry and topology of the objects.
All right, let's three. You can discuss or we don't have to necessarily, it's just a part to fill out. All right, let's go.
Thank you. Thank you, people on Zoom.